Okay, Professor Daniel Hallinan, I hope I pronounced it correct, is an associate professor at the Florida A&M University, State University College of Engineering, with interest in fundamental polymer physics of nanostructured materials, such as block copolymers and polymer grafted nanoparticles as well as applications related to energy sustainability. We're all listening to you.
Okay, thank you for the introduction. And you can see my screen as well?
Yeah.
Okay, great.
Great.
My presentation will be a bit of a divergence from most of the other presentations in this session. We're actually interested in dense membranes, so membranes that rely on the solution diffusion mechanism. These are non-porous membranes. I'll talk a little bit about potential applications, but more so we're focused on the fundamental properties of some interesting model materials that could be next generation membranes. This work was conducted by a PhD student who has since graduated and works at Intel now. And we collaborate with the University of Bologna in Italy. Professor Matteo Manelli is the collaborator. So first, I just want to mention my university and my College of Engineering. We are in the capital of Florida in southeastern United States. And we are a unique marriage of actually two universities, FAMU, which is a historically Black college university, and FSU, which is an R1 research school. And both are in Tallahassee, and we have a separate campus. And this is a picture of our College of Engineering. So just a little introduction to where we are before I talk about what my group has done. So this is just one potential motivation for water vapor transport in membranes. I discovered this interesting schematic in an article, and this is basically a schematic of a power plant, coal-fired power plant. And what really struck me was that the last step in this power plant is to basically heat the flue gas, basically the waste stream, what you're getting rid of, energy is put into. And the reason that that's done is to actually prevent condensation once the flue gas has been released to the atmosphere, raining back down into the stack. Other potential applications are drying of natural gas and treatments where you want to remove water vapor, and potentially, if you do that in the right sort of way, that water produced could be potable. But my talk is a little more focused on really materials, advanced materials for membranes. So block copolymers are a very interesting class of polymers for membranes that are have a covalent bond between two dissimilar polymers. So here I'm showing polystyrene, which is relatively hydrophobic and glassy at room temperature polymer, coupled with polyethylene oxide, which is quite hydrophilic due to the large number of oxygens in the backbone and has a low glass transition temperature, so it's rubbery. And if you make these materials to sufficiently high molecular weight and the polymers are sufficiently dissimilar, they will phase separate like oil and water, but because of that covalent bond, it's a single molecule, and so they can only phase separate on the length scale of the molecule itself. And so that's usually, because they're polymeric, tens to hundreds of nanometers. And depending on the relative ratio, the value of N and M of your polymers, you can get all these well-defined morphologies, is what we refer to them as, or structures, with this characteristic size D that's on the order of 100 nanometers. So I'm going to focus first on the lamellar phase, and we actually synthesized one of these polymers in my lab, relatively high molecular weight, so that it can make a dense freestanding membrane. The polystyrene, which is glassy, gives mechanical strength, and the polyethylene oxide provides hydrophilicity. And actually, these materials are also of interest for carbon dioxide capture. So we did X-ray scattering, which tells you about the characteristic domain size, the periodicity of the block copolymer, of the lamellae. And also so this primary peak tells us about that characteristic size, and the spacing of the primary and secondary peak tell us that it is lamellar. So we took this polymer and we did some studies on it. And the first thing we did was just some equilibrium measurements. We equilibrated it in different relative humidities, and then measured the degree of crystallinity. Polyethylene oxide is a semi-crystalline polymer. And we have a control here. So the blue squares are just homopolymer polyethylene oxide, and the red circles are the block copolymer. And you can see a couple things. As we increase the humidity, when we get up to high humidity, the crystallinity decreases significantly, which was surprising to us. We didn't realize that water could dissolve PEO crystals. The other thing you see is that the block copolymer structure itself, by confining the polyethylene oxide, results in, at any given humidity, a lower crystallinity. And crystals are expected to be impermeable, and so lower crystallinity should equate to better transport of water through the material. We also looked at another morphology of another block copolymer we synthesized, 92 kilogram per mole polystyrene, 45 kilogram per mole polyethylene oxide. So it's a majority polystyrene. So we have these PEO, we expect to have PEO cylinders in a polystyrene matrix, and that's what the X-ray scattering tells us. And this is, again, just that same lamellar block copolymer that I showed you before. So I'll refer to the cylindrical one as SEOC and the lamellar one as SEOL. And we see if we look at the melting temperature of the PEO crystallinity, a drop at high humidity. And if we look at the crystallinity again, here's SEOC, here's SEOL, we again see a drop at high humidity. It's a little bit more gradual in the cylinders. And actually, so there are three things to take away here. One, if we look at different temperatures, the increase in temperature causes a melting of PEO crystals. As we know, with any first order melting transition, increasing temperature causes it to happen. A melting due to increasing the water activity. And then also we see that at any given water activity or relative humidity, you can think of the scales as the same. The cylindrical morphology has even lower crystallinity than the lamellar. Confinement affects crystallization. All right, so what about the water absorption isotherms? So you can see here two different classes of water absorption isotherms without actually a big effect of humidity. At low temperature, the crystallinity allows less water to be taken up because the water can only go into the amorphous regions of PEO. When we're above the melting temperature, the purple and grays have a higher uptake of water. And actually you can see at 55 degrees C, this transition from the semi-crystalline material to the amorphous material. And what we can actually do is, if we normalize our water absorption to grams of the amorphous polymer rather than grams of total polymer, we can get a collapse here of all the isotherms at low activity. We don't get the collapse at high activity, and really we think the reason for that is that our measurement of crystallinity and our measurement of absorption isotherms are not analogous. Really, the degree of crystallinity, there's a lot of uncertainty because of just limitations of the measurement that I won't go into due to time limitations. The other interesting thing we found is if we did a Zim-Lundberg analysis, we found that water is actually clustering at these high humidities inside the polymer. So in other words, at low humidities, it's individual water molecules distributed through the free volume of the polymer, but at high humidities, it's clusters of water that appear to be present in the polymer. So in order to measure transport, one of the techniques we really like to do in my lab, because we can separately and directly in the same measurement measure absorption and diffusion, which for absorption diffusion based transport through membranes, the product of those two is the permeability. And so if you did a membrane permeation measurement, you get permeability, but we can get these two rather accurately and separately, solubility and diffusivity. So we have an infrared source, just like infrared spectroscopy, like you might use to determine the chemical composition of a material. It enters a high refractive index crystal, an attenuated total reflectance crystal, and it can have single reflection or multiple reflections, but then it exits the crystal and goes to the detector. And at each of the reflections, there is an evanescent wave that can actually detect and interact with the sample. And so we can place polymer membranes on the crystal and then control the other surface of the membrane, introducing dry air or humid air or even liquids, if we want to look at liquid-based transport. And so here's an example of an experiment. The orange or reddish spectrum is the dry polymer. And so you can see water stretching peak here. You can see many different characteristic peaks of the polymer, water bending as well. And as time goes by, this dry polymer has been exposed to 100% humidity. These water peaks increase with time. Each of these spectra at a different point in time through the course of the experiment. We can then integrate the area underneath the water stretching peak, for example, is the one we focused on, and plot that value versus time. Because we care about transport and not the absolute value, we typically normalize it. So each one of these data points is from an integration of a spectrum that's been collected over time. And we did a number of different experiments from the dry membrane to different humidities. And then this blue curve that's being shown in these figures is the best fit of a Fickian diffusion model. So the only adjustable parameter in the model is the diffusion coefficient, and that was adjusted to minimize the error between the model and the experiment. And you can see that the model doesn't actually fit the experiment very well in either of these experiments to medium to moderate humidities. Interestingly, when we go to higher humidity, the apparent transport, the apparent diffusion looks to be Fickian according to at least the agreement between the model and the data. And if we go to 100% RH, what we see is actually two-stage sorption. So we see a Fickian sorption and then a much larger sorption at higher humidity. We think that the second stage of sorption, which is much slower, but takes up a much larger amount of water, is due to actual swelling, macroscopic swelling of the polymer that doesn't happen at the.
Danny, we have 5 minutes left, and we wish to leave few minutes for discussion.
Great, I'll be finished in time. Thank you. So to try to understand why we saw non-Fickian diffusion at low humidities and then Fickian diffusion at higher humidities, we developed a very simple sort of reaction-based model, although it's probably not technically truly a reaction. So we have polymer crystals present in the PEO. We have water molecules diffusing into the material. And we proposed that the water molecules get immobilized as they dissolve the polymer crystals. And then once the polymer crystals are dissolved, they are amorphous. The polymer is now amorphous and the water molecules are again free to diffuse. Since all of our experiments were sorption, to simplify the model and reduce the number of fitting parameters, we assume that it was an irreversible model, so we don't need to worry about the back reactions, the back reaction rate constants. And so we just have these two, K1 and K2 are our forward reaction rate constants. And we can write conservation balances for each of the components in the system: the water molecules, subscript W, the polymer crystals, subscript C, and then the water polymer crystal complex, subscript CW. And so, of course, the crystals and the crystal water complexes are not diffusing, and only the water is diffusing. So the rate of change is on the left-hand side of these equations. The first term in the first equation is a diffusion term, and then there are two reaction terms. And if we non-dimensionalize this, you actually get quite a few dimensionless variables and dimensionless parameters, but I just want to focus on two. This Thiele modulus, which is just competition between diffusion and reaction, and just a concentration ratio, this lambda, which is the ratio between the final water concentration to the initial water concentration. So we saw this effect of final humidity. And if we do a parametric study, what we see is that when we're at lower humidities or lambda is small, if diffusion and reaction are of similar magnitude, such that Thiele modulus is about on the order of 1, then we see this apparent non-Fickian diffusion, very reminiscent of what we saw in the experiments. Whereas even when we're at this alpha of 1, when lambda is large, when we go to high humidities, everything appears to be Fickian. And so we think this really captures what we saw in experiments. I'll make one last comment before I conclude. We also did desorption experiments. And so in desorption, we don't have to worry about the crystals melting. And what we see is that the apparent diffusion coefficient from desorption is about an order of magnitude faster than sorption. And we think this is really the true diffusion coefficient of water in the amorphous PEO, because there's no immobilization affecting the apparent diffusion coefficient. So to conclude, we found that these amphiphilic block copolymers have thermal properties that are a function of water activity, and that was really our biggest contribution. I don't think that was realized before our work. We found that PEO crystals can be dissolved by water, and that the water absorption, the amount of water that goes into the polymer, scales with the amount of amorphous PEO, amorphous hydrophilic component. And that last diffusion, that last conclusion, I'll actually skip for the sake of time, and just want to acknowledge collaborators both in Italy and here in Tallahassee at High Performance Materials Institute, where we did some of our differential scanning calorimetry. Our X-ray scattering was done at Argonne National Lab in Chicago, or outside of Chicago. We had some help from some shops and some funding from the National Science Foundation of the United States. And that's my group, and thanks for your attention.
Thank you. We have time for 2 questions. We have one here.
Very nice talk, Dr. Daniel. My short question is, do you look at the plasticization of both the phases by water, by looking at the consumption temperature of the polystyrene and the PEO phases?
I'm sorry, I didn't catch the middle of that question. Could you repeat it for me?
Did you look at the plasticization of the phases by water? Maybe you can do it looking at the TG of both the phases, of the polystyrene and the PEO phases.
Did we look at the precise, and then I just can't get that one word, the precise what of the phases?
Just transition temperature, the TG of.
Oh, yes, actually we did. That's a great question. Yeah, so we did. And the TG well, PEO TG is actually really hard to detect. So we didn't look at the PEO TG in detail, at least within the context of the effective humidity. But we did look at the polystyrene TG. And what's remarkable is that it is actually depressed by a considerable amount. And we were really stumped by this for a while. And we did a whole follow-up study that we haven't actually published yet. But what we found is that homopolymer polystyrene takes up a detectable amount of water. It's not as hydrophobic as you might, as compared to like a polyolefin. And it takes up enough water that water actually depresses the TG by about 5 to 6 degrees when you go from dry to 100% RH. We also actually even measured the mechanical properties and the storage modulus that drops by about 50% too when you present that water. It's still strong enough that it's a freestanding membrane even at 100% RH. Even in liquid water, it maintains its mechanical properties enough, and that's one of the advantages of the block copolymer. So we couldn't measure PEO homopolymer at 100% relative humidity because it would absorb so much water that would actually dissolve and just become a solution. But the block copolymer does, it is affected by the water, but not so much that it isn't able to be, I mean, we've even done permeation experiments on it in another context. And so because it's high molecular weight and entangled, and the polystyrene is hydrophobic enough, as long as we stay below the TG of that polystyrene, it's a nice strong material. And of course, I mean, I think the interesting thing to do in our future work is to try to coat it as a thin film on a porous support, because that's really what would need to happen for any real membrane application of it.
Thank you. Daniel, can I have a very naive question from non-specialists? Do you have an in silico approach to sort of model all what you do ahead of preparing your crystals, so that you know all this measurement that you did ahead of the synthesis or the sort of making your crystals, so that you really adjust the reaction appropriately to get the dimensions and the pore size in the structures that you're looking for in a in silico modeling way ahead of any chemical reactions.
No, we did not, we have not. So there has been quite a lot of fundamental study of block copolymers and simulations of their structure. But most of that work has been done at quite low molecular weights. And to get really like beautiful structures that for example, like my schematic implied, and that you can see beautiful micrographs of, you really have to be at relatively low molecular weights. What I mean by that is maybe definitely less than total molecular weight of 100,000, probably more like less than 50,000 kilogram per mole. We wanted to, there was this gap in, and the simulations sort of tell us how that domain size will scale with molecular weight. More of what motivated where the molecular weight and composition we shot for was that we found in prior work that you really need about a 50-50 fraction to get that balance of mechanical strength and high selective transport of species. And so that's why we targeted mainly the lamellar phase, and then we targeted high molecular weight polymer, because really, if you're not at high molecular weight, you don't have sharp interfaces between the two blocks, and you also don't have enough chain entanglement to really get a strong material. And without sufficient mechanical strength, it's really hard to do any sort of membrane testing. So no, we didn't do any simulations. There's been some work done on block copolymers generally, but we're always looking for people to collaborate with for simulations, because that's really not our.
That would be fantastic. That would be fantastic. Well, one last question. What time is it now where you are?
It's 10:38 where I am.
Okay, have a good day. Thank you so much. It was really
Thank you. Thanks for your questions.
Thank you so much.